Hello. Today I want to show you how to do simulations using Runge-Kutta. Usually the Runge-Kutta is part of a library in a math package that you might use, but in some cases, if you're doing embedded programming where you need to put the code, the differential equation solver, into firmware, you're not going to be able to use a library, so I want to cover Runge-Kutta specifically. And one of the reasons why I like Runge-Kutta is because it's simple and it's restartable. It's easy to restart in case you hit a boundary condition, whereas some of the other methods are not so easy to restart from like say, for instance, you hit a boundary. So to get started, uh, basically what we're trying to do is in simulation is to integrate a number of variables. In this case, I got position, velocity, and acceleration. And what's happening here is that I'm calculating out the rate of change in the position, velocity, and acceleration. And you can see that the rate of change in position is just the velocity, and the rate of change in velocity is acceleration. Rate of change in the acceleration is the jerk. So I can calculate out the jerk here using the state that was passed to it, which was position, velocity, and acceleration. So you got the velocity, acceleration. The position doesn't make any difference right now, and this is the control output, which I have fixed at 50%. And because my model has an open loop gain of 10 millimeters per second per percent output, a 50% output will make it go 500 millimeters per second. The damping factor and natural frequency will just determine how I get to 500 millimeters per second. I have a loop time in milliseconds, and this is my control output. Okay, so let's go down and see the results. Now here I'm using RK fixed, which is a built-in function. I don't really think you need to pay too much attention to that except for it's built in. Whatever library you are using, it will have probably a different name for it. But what it returns is time periods, and you got the time, position, velocity, and acceleration. And then this could be plotted out. So here you can see the position, the velocity, and you can see that the velocity is about 500 millimeters per second over here. And on this side, you can see that this is about 500 milliseconds. This is the velocity on this side. And then this is the acceleration. And this is letting me do a simple open loop simulation. So let's talk about the Runge-Kutta itself. Okay, to begin with, it's easy to get started by using Euler's method. And Euler's method is very similar to how principals or interest is calculated in a bank. And it used to be in a bank, you'd put in $1 and you might get 4% interest on it. And at the end of the year, you got $1.04. And that's basically what's happening here, is that we have this function that the delta t is the time, and you just calculate out the rate of change given the interest rate, and then you get $1.04. Now, that works okay, but it assumes that you are getting the same interest for the whole year. And that's not the way that it usually works, or at least in simulations, it doesn't work that way. An improved Euler method takes 2 points. You have the initial slope and the final slope, and you average them out to get a better approximation of the slope, and usually you get a much better answer this way. And this is fairly simple to use, and but it's still not very good. And then this is Runge-Kutta, and the reason why I want to show you this is because it's very simple to implement. It's just a few lines of C or whatever code you're using. And what you're doing is you're calculating the slope. That's these K1s, K2, K3, K4, 4 different times. You have one at the beginning, 2 in the middle, and 1 at the end. And then you're averaging them together. And it's kind of a weighted average. So the first one gets counted once. The 2 middle slopes get counted twice. and the final slope gets counted only once, then you divide by 6. And you can see that this is for the whole time period. This is, or starting at the beginning of the time period. This is halfway, and this is another one halfway, and this is n plus 1, or the time period plus 1. So that's your final time period. So you calculate 4 different slopes. Now, K1 in a normal example, like what you get in college, is just a variable, but normally it's a vector. And in that previous example that I showed you, it is a vector. So it's a position, velocity, and acceleration. And in some cases, I have up to 9 parameters that I'm integrating for doing a hydraulic system. So I have spool positions, velocities, pressures, accumulators, pump, flow, all that kind of stuff. And anyway, let me just show you the integrations here using the 4 different methods. Now, this is the perfect solution over here. I've solved that manually someplace else. So you can see that the simple Euler method doesn't do very well. Here, the improved Euler method does a lot better for not much more effort. And you can see the Runge-Kutta and the perfect solution are almost identical. I think they are identical. And I can improve the simple Euler method by reducing the number of or the time period. So let's take the time period and make this let's see, a 0.5. And you can see that as I make the time period shorter, the integrations get to be much more accurate. But the problem is now you're doing twice the work. The question you got to ask yourself is doing, here you're doing 4 times the solving to get the answer. Can you get by, or is this solution going to be 4 times better than this solution? And you can make the iterations too small, so you end up doing an awful lot of work for nothing. Let's just make this a little bit smaller. And you can see that the simple Euler method does not work very well, but the improved Euler method works very well. So reducing the time periods makes a difference. But with Runge-Kutta, you can have fairly coarse time periods, and because you're doing the 4 approximations, you get a much better solution with fewer iterations. So let's go back to the position, velocities, and accelerations. This is a vector that, and this would be one of those K1 vectors internally on this RK fixed. So the K1, K2, and K3 vectors, each one would have a velocity, a position, velocity, and acceleration. And to see how this works in a real simulation, I'm going to go to my hydraulic simulation here. My Y vector is now 9 parameters. I got a spool position, spool velocity, pressure on the A side, pressure on the B side. Now, I don't really care if you look at this, see all the detail and try to understand this, because it's a little bit overwhelming, but I just want to let you know what can be done. I can blow this up a little bit here. Got initial velocity of the actuator, that's the piston. Initial position of the actuator. The control output, I can implement a PID using differential equations too. And I got the pump volume and the gas volume. And the gas volume is used to calculate the pressure in the accumulator. So this is the state. And then I do some calculations. These are calculating out the rates of change. And the result, coming on down here, it takes a second to do all the calculations because it's quite complicated. Come on. There we go. So now we have the time periods, spool position, velocity, spool velocity, pressures, the accumulators are in the cylinder on the A side, pressure on the B side, which is rod side, the velocity and position of the actuator, the control output, and the flow of the pump. So now I can plot out all these parameters of the simulation. What I like about using Runge-Kutta is that I can simulate nonlinear systems. I can simulate impacts like what I've done right here, whereas it's kind of hard to do in state space or using Laplace transforms. And finally down here, you see this is the accumulator gas and the accumulator pressure. You can see the flows and the pressure in the cylinder, and here is the position control and the velocity control. And I have actually used this simulation for doing a simulation for a diesel system for the Department of Energy. Anyway, the big thing is Runge-Kutta can integrate differential equations. It can integrate nonlinear differential equations. It's much more flexible than Laplace transforms. Runge-Kutta is restartable, which means you can start it halfway in a time period fairly easily. And it's easy to implement in embedded firmware. So if you have any questions, just ask them below.